Good morning. Happy Monday. The good news, we'll start with the bad news. The bad news is that there is an exam on Monday. The good news is that there are only 2 more days of new material before that, today and Wednesday. Then we'll review on Friday. And then there are only 2 more days of new material after that before the final. So Wednesday and Friday next week. Today I would like to start wrapping up our discussion of nanobiotechnology with a discussion of some of the classic demonstrations in nanobiosensors. And we are going to find that, that a device that we've met earlier in the course, a field effect transistor, serves as the basis for a wide variety of types of nanobiosensors. In particular, if you have a semiconducting film that can be gated either by an external or an internal gate or by stimulus from some bound protein or ion or proton from, for example, pH or lack of protons. And the channel itself can be a wide variety of nanoparticles or thin films. It could be a thin film of a semiconducting polymer or a conventional semiconductor, or also nanowires of conductive polymers or other types of materials. And so let's look in a little bit more detail at what are the design criteria that we might run into, or the modalities that we might run into and that we might need to engineer for. The first is form factor. And form factor is a word that I first heard in a Bill Gates interview from about 10 years ago, where he was talking about the form factors being the next frontier of innovation in electronic devices. And he was particularly talking about, at that time, the Zune, which was a knockoff of the iPod. Form factor just means, is it rigid, flexible, stretchable, thin film, nanowire? What is its form and its mechanical properties? So a rigid sensor could be like an on-chip device. A flexible sensor might be something that could conform to the skin, but it doesn't conform as well as something that's stretchable, because flexible just means that it tolerates bending strains, but stretchable means that you can actually supply a significant amount of tensile deformation to it. Flexible will get you wrapping around cones and cylinders, but not anything complex like human skin or internal organs. If something is sufficiently thin and flexible, it might still be able to adopt complex topographies, but there will always be wrinkles in something that's only flexible and not stretchable as well. Flexible implies thin film, because as you make something thinner, you make it flexible. Even the strongest materials known to science are still flexible if they're sufficiently thin. And I put nanowire up here, not that this is necessarily a form factor, but there are many ways in which we can use nanowires technologically. For example, in thin films of nanowires that are deposited on a surface that allow a percolated pathway from one end or from one electrode to another, or also if we have single nanowires that offer, for example, single molecule sensitivity to analytes. Now, how about the physiological signal? So the biological systems produce and are receptive to a wide variety of signals, and here are some examples that I want to highlight. So electronic signals, voltages produced by or which produce action potentials in myocytes, for example, muscle cells and neurons. You have ionic conduction, which is how neurons do indeed operate. Mechanical signals, as we know, touch receptors in the skin, and also just the movement of the body produces mechanical signals. And optical signals. We don't usually generate optical signals unless at least in the visible regime, unless we're Cyclops from X-Men. But in some cases, some biological organisms do generate optical signals. But we certainly take in optical signals. Our eyes are one of the more useful senses that we have. How about the power source? If you have a biosensor, particularly in wearable and implantable devices, how are you going to power it? We have external sources of power, which is where you take just the battery, or you plug it into to an outlet in the hospital, and then you have wires that go onto your wearable device or inside the body. Now that could potentially be a source of infection, and hospital-borne illnesses can be transmitted through the skin, through the wires, which is problematic in implantable devices. And so wireless and passive systems, and we'll see an example today of a wireless passive system where we have some kind of electric field that induces a current and supplies power, for example, through the skin to a device. And in active power sources where we might have, say, onboard solar energy harvesting or piezoelectric devices. Piezoelectric devices are devices that give you an electrical impulse, an electrical signal with a mechanical stimulation. How about transduction mechanisms? How do you transduce a signal from an analyte or a signal to the device? You can have capacitive mechanisms where you have an electrical charge on one side of a barrier and it induces either the accumulation of charge carriers on the other side of the barrier in the case of, say, a field effect transistor, or alternatively you change the capacitance of a capacitor, for example, with a compressible or otherwise modulatable dielectric device that changes the capacitance, and the capacitance can be read out as a signal. Also, resistive sensing, or resistive transduction mechanisms. Resistance can change with a mechanical stimulus, that can change with a magnetic stimulus, it can change with an optical stimulus. And you can have optical transduction mechanisms. And there's an example of a device that's sort of all optical. I don't have a slide on it, but for example, suppose you wanted to make a pressure sensor through a dielectric slab that was compressible, and you had, say, an LED on one side and a photodetector on the other side. You could actually pinch the dielectric elastomer to attenuate the signal going from the photodiode to the photosensor. So that could be an optical method of transduction. Optical methods of transduction could also include plasmonic effects, which we'll talk more about on Monday. And plasmons being a form of energy transfer in which a photon is coupled to the conduction electrons in a metal dielectric interface to go from one end of, say, a nanowire to another. It's called a surface plasmon polariton if it moves, and it's just called a surface plasmon if it's stationary. And finally, the location determines determines basically everything else on this list, whether or not it's external or internal. We need to determine if it's external or internal, if it needs to be biocompatible so as not to induce a rash at worst, or at best, or degrade into toxic byproducts at worst. If it's biocompatible, is it also resorbable? Like resorbable sutures, for example, that are made of hydrolyzable polymers that can be stitched in the body and then dissolve at some programmed time scale. Or if it's not resorbable, and suppose it's really futuristic, and we have a prosthetic device, like a limb or artificial skin, would it also self-heal, and would that be beneficial? So this is not really used technologically, but it's certainly on the horizon. Okay, so let's talk about organic field effect transistors, and or not just any type of field effect transistors in a little bit more detail. So this is a schematic diagram of an FET, and we met this earlier in the course when we were talking about semiconductor manufacturing. And you have some substrate with a conductive gate, an insulator. This is called the gate dielectric. Then you have some semiconducting material, which is sometimes called the channel, although strictly speaking, the channel doesn't form until you apply a voltage to the gate electrode. Then you have a source, which is always grounded. So the source is the source of all the charge carriers that are sucked into the semiconductor based on the bias at the gate. And then you have a drain where the charge carriers drift to once you apply a drain voltage. Okay, so usually what we use for test devices is a highly doped silicon wafer. Now, why? Because it's super flat and it's easy to do the chemical processing, the photolithography and everything to make the source and drain electrodes. So we use a highly doped silicon wafer so that it's conductive, almost as conductive as a metal, and that's usually used as the gate electrode. And possibly also the semiconductor, and also the gate dielectric. So you can have just a regular solid silicon wafer, and you can grow an oxide film to give you your insulator dielectric layer, and then you can apply your semiconducting material or nanowires or whatever your semiconducting channel is on top, then evaporate your source and drain electrodes or have them pre-patterned, and then you're good to go. In the case where you're testing silicon itself, you can start with what's called an SOI wafer, which is a silicon on insulator wafer, which is manufactured in such a way to give you a highly conductive substrate, then an insulating oxide film, then another semiconducting layer on the very top, and then all you need to do is apply your source and drain electrodes and you're good to go. So first thing that has to happen is that the voltage, the gate voltage, V sub G, is ramped up, and then the first charges are injected from the source into the semiconductor, and that's given in panel B. And what happens is that the channel at first, the charges that enter the channel, particularly in sort of next generation and printed types of semiconductors, there are trap states that need to be filled. For example, if the charge carrier is negative and we have some oxidized bits in our semiconducting layer, then the oxides will actually suck the holes to them, and those electrostatic interactions within the semiconducting layer need to be satisfied by the flooding in, by the flooding in of the charges from the source in order for any of the subsequent charges to be mobile within the layer. So the voltage that fills all the traps and that allows you to have some mobility of the charges after you've filled up all the traps is called the threshold voltage. So the VG needs to be greater than the threshold voltage in order to have mobile charges in the channel. So negative gate voltage means positive charges are injected and vice versa. And the number of charges that are injected is proportional to the gate voltage and the capacitance and thickness of the dielectric insulating layer, which kind of makes sense. So we apply a positive voltage here and negative charges, so electrons come in through the source and vice versa. Okay, next thing that happens is that at a given gate voltage, and this is in the output modality of this measurement, where we have a fixed gate voltage and we ramp the drain voltage. As we have a fixed gate voltage, the drain voltage is ramped and the current is linear until the drain voltage equals the gate voltage minus the threshold voltage. And at larger drain voltages than this, we have a situation where there are competing electric field lines. So we have charges of the same biases of the same sign on both the gate electrode and the drain electrode. And what we have is mathematically somewhere in this channel where the field lines cancel out and there is no electric field. And when this happens, that means that the saturation point is reached. And what you see in the curve for the current measured at the drain versus the drain source voltage is that the current stops increasing, and then as you ramp up the drain voltage even more, the drain current does not increase anymore because you've pinched off the channel, so to speak. And this is called the saturation regime. This is the linear regime. This is the saturation regime. And the conductivity in the channel is, the upshot of this is that the conductivity in the channel is, of course, mediated by the gate voltage. You have a larger gate voltage, the greater the conductivity is going to be, the more charge carriers you're going to inject into the semiconductor, and the more you can, current you can get out of it. Yes, sir.
In our graphs here, VDS stands for the threshold drain voltage.
VDS is the drain source voltage. It's just the voltage between the drain and the source. Now, okay, why spend so much time talking about this? The reason is that it's the basis of pretty much all electrical biosensors, the field effect transistor. And we can modulate the conductivity in the channel not just with an internal gate voltage, but also with charged species that dock to the semiconductor. So if you have a semiconductor that binds, say, a particular protein, and the protein is charged, then that charge will induce a conductive channel within the semiconductor, and then you can measure the change in current, for example, with a certain amount of analyte that's bound to the semiconducting layer. And I should point out that it doesn't just have to be this arrangement. The field effect transistor geometry is quite versatile. You can have any combination of these. This is bottom contact, top gate, bottom contact, bottom gate, top contact, bottom gate. And the contacts refer to the source and drain electrodes. Now, we can use this information, and don't worry about this for the exam. Just know that it's in principle possible to derive this information. You can get a property of the semiconductor called the mobility, mu, and the mobility refers to the ease at which the charge carriers will move within the semiconductor. And if you plot for example, the log of the drain current versus different gate voltages, then you can, or actually this is in this regime, and you can calculate it for the linear regime or the saturation regime. Saturation regime is more common. You use this equation and you find the slope of this, and the slope is related to the geometry of the field effect transistor. It's the width and the length times the saturation mobility. And the mobility, people say that it's sort of an intrinsic property of a material, of a semiconducting material. Really, it's an emergent property due to the fact that you measured it in a device. It's not like melting point. It's like the mobility in a particular geometry. So sometimes these numbers are given a little bit more credence than they ought to be, but in any case, it's often used where, say, you make a bunch of nanowires and you calculate the mobilities in each nanowire. Yeah.
Is there like a standard test geometry for documented mobility values?
Yes, for different classes of materials, there are different standardized methodologies. Okay, so how about one particular class of nanostructure, and nanowires are quite important in the research lab, but also increasingly technologically. And these are in some referred to as one-dimensional nanostructures because they're long compared to their cross-sectional dimensions. And you can have many different ways of creating one-dimensional nanostructures. You can have, for example, structures whose building blocks have an anisotropic crystalline morphology where it selectively grows along one axis as opposed to the other two. You can have interphase growth. This is called the VLS, vapor liquid solid method, where you pattern, for example, catalyst particles on a surface, say a metal catalyst, and you pattern it by photolithography. Then you add in, you melt it, and then you add in chemical precursors. And the chemical precursors are converted catalytically into the structures underneath. So it's like taking the skyline of Manhattan or San Diego, and the high rises all kind of grow where you've patterned kind of the footprint of the device of the structures. You add in the vapor, and the vapor causes them all to grow. Then you can break them off and harvest them or not. Sometimes these structures are used directly on the substrate on which they're grown. This is a templated synthesis, which is sort of robbing Peter to pay Paul, because you need to be able to pattern the dimensions of the nanowire using some external technique like e-beam lithography. Then, for example, you use electrodeposition or some other process to grow these particles that eventually form a one-dimensional nanostructure. D is quite similar to A, except that in this case there's no intrinsic or only a weak intrinsic preference for the structure to grow along a preferred axis. But if you have some capping group, this could be some organic material that you load into the reaction vessel, it will bind to particular facets of the growing crystal so that you can influence the material to grow in only one way. This is solution phase synthesis with an organic capping reagent. You can have self-assembly of zero-dimensional elements. So zero-dimensional really means like buckyballs, like C60, or quantum dots, or any small nanoparticles that have some preferential ability to align. This could be either some intrinsic ability to align, or perhaps some extrinsic motivation to align. For example, electrophoretic alignment, where you have a strong electric field in a solution, and then you create dipoles in the individual particles, which self-assemble then into one-dimensional nanostructures. And you can also have size reduction. How about literally squeezing or cutting an object to form it into a small nanostructure, almost like metalworking, but at a very small scale. Okay, once we have these nanowires, assuming that we made them in some bulk synthesis method, how do we get them to interact with each other? So sometimes you might have two types of nanostructures that have different properties, and you need them to be able to communicate with each other, say in physical contact or close physical contact. So suppose our goal was to cross two nanowires at 90 degrees, crossing streams in the words of Ghostbusters. So suppose we deposit nanowire A just by sneezing some particles on a surface, sneezing these nanowires on a surface. Then we deposit nanowire B, and then we search around for the geometry that we want. And this is no, we don't have it here. Almost, because they're kind of touching at the end. Sort of, they're not at 90 degrees, although there is some overlap. And then this one, we finally say close enough, because what are the odds that you'll find two that are exactly crossing at 90 degrees? And why would you want to cross nanowires at 90 degrees? Suppose you wanted to do photonic and plasmonic transduction mechanisms in the same nanostructured device, or suppose you wanted to couple quantum dots to nanowires, and we'll talk about these applications on Wednesday when we talk a little bit more about light confinement using plasmonic nanostructures. But anyway, there are some methods of doing this deterministically or quasi-deterministically as well, and these references are now old, but these methods are still used. One is flow-driven alignment, where you use the shear that is produced by flow in a microchannel in order to influence the nanowires to align themselves along the axis of flow. And if you do this in two perpendicular directions, you end up with crossing nanowires. You can use optical trapping mechanisms where you change the dielectric environment in the vicinity of the nanowire, which causes a polarization in the nanowire that produces a motion in the nanowire. Don't worry about the details here. There's dielectrophoretic alignment where you apply opposite voltages to these electrodes, and there are nanowires in this channel that you can kind of see here, and the nanowires line up in parallel to the electric field lines. This method is probe-based manipulation, where you actually take an AFM probe tip, and that's an atomic force microscope probe tip, and you kind of kick around the nanostructure until you get it in the spot where you want it. And this work was actually done by a member of our faculty, Don Serbely, now in ancient history, when he was a student. Sorry, Don, just kidding. And we have optoelectronic tweezing, which is similar to the, it's kind of like taking optical tweezing and dielectrophoresis at the same time, where we create a dipole in a photoconductive layer that produces an electric field within a liquid solution, and then we create this dielectrophoretic structure, but we've induced it using an optical signal. Okay, here's like the first example of a biosensor for a protein that highlights some of the important characteristics. And in this case, we used, these authors used an organic semiconductor that had been modified with avidin, which is a protein which has a very strong affinity to something called biotin, which is a small molecule. And what they found is that, well, if the biotin binds, it will change the electrical conductivity. And in these extremely noisy data, but this was a first effort, so good enough. They found that indeed the electrical resistance changed in a more or less predictable way. Now we can do this a lot more sophisticatedly with silicon nanowires, and these ones were grown by the vapor liquid solid growth mechanism, so the downtown of San Diego method. And this paper was published. This is now like 15 years old, but it was the basis. But it's been cited thousands of times. It's the basis for basically all of nanowire bioelectronics, from Charles Lieber's group at Harvard, and Yichue, who is a graduate student at the time, who's now a super famous professor at Stanford. And what they did was they took this nanowire and evaporated a source and drain contact on a bat gate. The bat gate is just this highly doped silicon wafer. And then the green is the dielectric layer. So then they converted this nanowire FET into a nanosensor by chemically modifying it with this amine terminated group. Now, what do we know about amines is that they're sensitive to acid. So if you add acid into them, the amines will protonate because the amines are a base, right? So if you have a silicon nanowire that's terminated, so silicon in the outdoor environment or the laboratory environment always has an oxide skin on it. So we have this oxide skin, which we can react with this silane monolayer. This is called aminopropyl triethoxysilane, which was grafted to the surface of this SiOH. Then in the presence of acid, so low pH, this is protonated. At neutral pH, it's not protonated, but we still have these hydroxyl groups on the or these silanol groups on the surface of the nanowire. And then as we increase the pH to make it very basic, we snatch these hydrogen atoms off to give these negative charges. So here it's positively charged, neutral, and then negatively charged. So what do we know about the transconductance, that is the way that the conductivity of a semiconductor changes with respect to the charge? Well, we know that we can modulate the gate, we can modulate the conductivity of the channel. So here is the conductance. That's just the slope of the current versus voltage curve at different levels of pH. So low pH to higher pH here. So this is a great pH sensor. There were already pH sensors in existence before we did it in this really sophisticated way, but we can do much more interesting things with this. For example, detect single virus particles. So suppose, or not viruses yet. We're going to start simple. We're just going to sense proteins in general. So I told you about the affinity of biotin with avidin or streptavidin, which is one of the strongest protein ligands. So a ligand is just something that binds to a protein. Biotin, streptavidin is one of the strongest interactions in all of biochemistry. So if you graft the biotin on the silicon nanowire and then you flow through streptavidin, which is charged, it binds to it and it changes the conductivity at the point where you add the protein. Okay, now the world does not need another streptavidin sensor because everybody, as soon as they make a new type of protein sensor, they always use this because it's pretty much guaranteed to work. You can also bind an antibody. So this is an antibody that's been produced by immune cells in order to bind to biotin. So it's not streptavidin, it's called antibiotin, and you get the same sort of effect. Antibiotin is an antibody that's charged, and instead of having a gate, it induces electrical charges to enter the channel just capacitively sort of through the solution. You can also, instead of binding a small molecule to the nanowire, you can bind a protein to the nanowire. In this particular case, what was bound to the nanowire is a calmodulin protein, which binds calcium ions. And you can see that if you flow calcium ions, which are positively charged, you induce a change in the conductance. And that's what's seen here. Now, how about electrical detection of single viruses using nanowires? This is by the same research group, and this is a schematic diagram. It's often fun in scientific research when you have a schematic diagram and you show the expected data that you hypothesize that you'll get, and then the real data magically looks like the hypothesized data. Sometimes the hypothesized schematic diagram is drawn after you have the real data so that it matches better. I don't know what they did in this case, but it's striking. So in this case, we have these antiviral antibodies on nanowire 1 and nanowire 2, and they're sensitive to different kinds of viruses, so they're selective. And if you have the viral particles and you flow them through, in this one, the green ones are anti this, then it will bind to the green ones and the conductance will change. Whereas the conductance in the blue nanowire will not change. And what do the real data look like? Well, first, they did some electrophoretic alignment. First of all, they took these structures that were lithographed by electron beam lithography, so everything comes together. Electron beam lithography, and in each particular junction, I guess right here, we have nanowires that are crossing between the source on one side and the gate on the other. So source on one side and drain on the other. Source here, drain here, nanowire here that was aligned electrophoretically using these fabricated contacts. And what do we get? Well, we have two different kinds of viruses and two different kinds of nanowires that are modified with the correct antibodies. And this is amazing to me that this worked, and it was kind of a while ago, 13 years ago now, but it's quite impressive. So this is the flow through of two different types of antibodies, and you can see that they or two different types of viral particles, and they bind at different times, giving you these predictable changes in conductance of the nanowire field effect transistor. Okay, how about more macroscopic forces? So for example, pressure. There are a lot of reasons in physiological monitoring why one would want to measure pressure. For example, intraocular pressure, pressure in the bladder, pressure for electronic skin, pressure in the intracranial space. So for example, after someone suffers a traumatic brain injury, they can have a head trauma that doesn't manifest for several days until after leaving the hospital, and then they get severe brain swelling, and they can die from that even though they've left the hospital. So what if you had a device that could go in the brain and monitor the intracranial pressure wirelessly and without a power source, and then over a certain amount of time it would dissolve away and you wouldn't need to go back to the doctor for a special kind of surgery. So we're building up to that capability here, but what's needed first is some type of stretchable and conformable dielectric layer. And what was used in this particular example was making a silicon mold, and it's mold because it's in a Nature journal, which is British, and that's how they spell it there. So you have the SI mold with inversed features, and you cast the PDMS on the mold, and then you take the PDMS out, and you get these arrow-like pyramidal structures. Now, how did you get these pyramidal structures? Well, if you have the right crystallographic orientation of the silicon and you pattern it by photolithography or e-beam lithography, and you etch the silicon with potassium hydroxide, you'll actually get these structures automatically. So it won't etch straight down, it'll etch in these inverse pyramidal shapes, which is pretty cool. Okay, then you bond an ITO slide, or an ITO on polyethylene terephthalate backing to it. ITO is indium tin oxide that we met when we were talking about solar cells. It's a transparent conductive film. And what happens is that if you have the structured dielectric, you get much higher sensitivity, so the capacitance changes as a function of pressure, and it's very sensitive for the case where you have these pyramidal structures. More importantly, if you have an unstructured film, you get this sort of weak recovery. So you put the weight on, the capacitance goes way up. Then when you release the stimulus, in the case of the structured lines and pyramids, so these are these pyramidal lines and pyramids, the capacitance goes all the way down within a couple milliseconds, whereas the unstructured film takes a long time to relax because it doesn't have any space for its structure to sort of ooze into and out of. It takes a long time for these polymer chains to move past each other to reach their equilibrium position. Yeah.
So is this function of capacitance due to actual surface interactions, like the pyramid structure, as pressure increases, kind of compresses and has more surface area? That's a good question. I didn't really say this. So the reason the capacitance goes up is because we're literally squeezing a capacitor. Just squeezing the capacitor, we're making the distance between the electrodes and the parallel plate capacitor shorter, so the capacitance goes up. Just from second quarter physics, when we talk about capacitance, and we have A over D, and D is the distance between the two parallel plates. So we can measure, for example, the weight of a dead fly. Died naturally, I'm told, in the lab. And we can also use this is the important part, is we can measure the charge transport properties through a single crystal of this guy, which looks like a house centipede with tennis rackets for arms and legs. And it's called rubrene, and we put it over the source and drain with this microstructured dielectric. In this case, they're square pillars, and you press down on it, and we have very fast response and recovery times. And we can, now this here, these are these output plots, but we're not changing the gate voltage externally. We're changing the distance between the gate electrode and the semiconductor layer. So this is a super sensitive pressure sensor, one of the most sensitive pressure sensors that has ever been made. And you can take, say, a thing with toothpicks in it, and you can measure where the pressure is, and very little crosstalk as well. You can take devices like this and you can strap them to your wrist in a Band-Aid, and you can get the pulse pressure waveform from the radial artery. And this work I was peripherally involved in. You can take these structures and you can implant them in the brain as well to do continuous wireless pressure monitoring and mapping with these ultra small passive sensors. So this is an inductive coil. It's copper in this case. And this is styrene, butadiene, styrene, triblock copolymer, elastomer in between, and the rubber is patterned with these pyramidal structures so that you have increased sensitivity and also recovery time. And this is kind of what the device looks like. And that's on Eisenhower's face. And yeah, so small. Now, where does it really get cool? Well, we can measure the pulse pressure again, and we can do it wirelessly. See no wires here at all. But more importantly, we can put this in a mouse brain, and then if you press on the belly of the mouse, the pressure inside the brain increases, which can be measured by a change in capacitance. So very recently, a group led by John Rogers and Daehyung Kim actually published a development of this device where all the components were biodegradable. So you had this wireless, passively powered through the skin using induction, which both supplied the power and read the signal out, device that was also biodegradable. So you put it in the brain, it dissolves over some programmed timescale. Now we can use nanomaterials for this kind of device as well. So this is a carbon nanotube that we can dope with this oxidizing agent called F4TCNQ, which sounds like a droid on Star Wars. And so if we take these carbon nanotubes, now carbon nanotubes, when you grow them randomly, they're a mixture of semiconducting and conducting carbon nanotubes. Conducting carbon nanotubes are the minor component. Conducting carbon nanotubes are about 1/3 of the total number, because there are a lot more ways to create a carbon nanotube in a chiral geometry. That is to say, when you take the chicken wire, that is a sheet of carbon atoms, and you roll it up to form a carbon nanotube. That's not actually how carbon nanotubes are made, but if it were, you take the sheet of carbon atoms and you roll it up. If you skew the sheet, you get a chiral nanotube. Now, chiral nanotubes means that there's a helicity to it, and that's what you get if there's a skew to it. Now, if it's a chiral carbon nanotube, it's more likely to be a semiconductor as opposed to a conductor. And the aligned type of carbon nanotube that has no chirality is a conductor. It's basically like a really thin metal wire, but it's made of carbon. So it's really a statistical argument that says conductive ones are less. Nevertheless, if you have some randomly deposited carbon nanotubes that bundle up into these bundles, you can actually, the whole network is conductive because there are enough conductive ones to supply conductivity to the entire film. So the idea here was to make a carbon nanotube film that was reversibly stretchable. So you stretch it out and you stretch these anisotropic nanotubes into this in situ stretched image, and these are atomic force micrographs of these carbon nanotube bundles. And then when you release the strain, these carbon nanotubes are buckled, but they're primarily buckled along the axis that was strained and then released. And because of this effect, you can restrain these carbon nanotubes by stretching them out, and then they fold back up, stretch them out, they fold back up. And because they're like this, they can now accommodate that strain without breaking connections in between the nanotubes. Yep.
Are these deposited on a stretchable medium that's used to do this testing?
Yeah, these are deposited on PDMS, which is a silicone elastomer, and it's been modified by ultraviolet ozone oxidation. Yep.
Generally, how long is a carbon nanotube compared relative to the radius of the nanotube?
That's a good question. Carbon nanotubes have been made that are up to 1 millimeter long and as small as a few hundred nanometers. The diameter of a carbon nanotube is on the order of nanometers. So 10 to the 7 aspect ratio at maximum. But aspect ratio in the business of semiconductor manufacturing usually doesn't refer to long and thin items. It usually refers to things that have a small line width relative to their height. Just in case you go to your job and you say, that's a high aspect ratio structure, they'll say, you mean it's long and thin? Yeah.
The more you stretch this, the more it aligns that axis, or is that only the first time you stretch it?
Yes, the more you stretch it, the more it aligns. But as you stretch it and it aligns, you also break more connections in between the nanotubes. So you sacrifice some of the conductivity for the stretchability. So in this plot, what you do is plot the resistance versus the strain. As you increase it the first time, the connections between the nanotubes break apart. Then when you bring it back to zero strain, the resistance stays along this path because you've buckled the nanotubes. But then you bring it past the strain at which it was previously strained, and then the nanotubes start to straighten out even more and break connections between the nanotubes and so on. Then it has the same behavior all the way up until this point when the silicone elastomer snaps. And how do I know that? Because I made this plot. So you can also stretch and relax these devices many, many times. This is to about over 10,000 cycles of stretching. And what it allows you to do is to make stretchable capacitors using these transparent films of carbon nanotubes. And this demonstration was the first stretchable transparent pressure sensor. Now, and we still don't have that capability in our iPhone because our iPhones are now pressure sensitive, but they're not stretchable. So there it is, that's what it looks like. And how do they work? Well, we shorten the distance between the conductive films, and there's this silicone elastomer in the middle, and we press down and we get this change in capacitance, which can be registered in either a compressive modality or a stretching modality, and you get exactly the same kind of data. And this is a pressure on the center pixel and the response measured by the 4 closest neighbor pixels. And you can see that the pressure here is a lot, or that the signal is a lot higher where it was actually pressed because the materials are stretchable, so we don't have crosstalk. If these were not stretchable materials, the whole device would compress no matter where you pressed it. All right. We'll take a question, but 20 seconds only. Later? Okay. All right, thank you, everyone.